So far, we've been pretty lucky, and everything we've talked about has interacted really nicely with limits and derivatives. For example, the limit laws told us that the limit of a sum, product, or quotient of functions was the sum, product, or quotient of the limits, right? There was this nice interplay where we could freely exchange the order of operations. Similarly, derivatives played nicely with sums and scalar multiplications. So a natural question to ask is, does the derivative of a product of functions equal the product of the corresponding derivatives? Mathematically, if f and g are differentiable at c, is the derivative of f times g equal to f prime g prime? The answer is definitely not. And I'm going to take some time to really highlight this because I don't want you to see this formula and accidentally think that it's correct. Now we can check this with a quick example. Let f and g both be the function which maps x to x cubed. The derivative of both of these functions is just 3x squared, and their product is the function x to the power of 6. Now the derivative of their product can easily be computed to be 6x to the power of 5, and we know that from the power rule. So in this case, we know what the answer should be. Let's check what happens if we multiply the derivatives. 3x squared times itself is 9x to the power of 4, and if you look at these two things, they look nothing alike. Their coefficients are different, they have different degrees, nothing has worked out as we hoped. So something more subtle is going on here. The theorem which tells us how to differentiate the product is called, unsurprisingly, the product rule. If f and g are differentiable at c, then so too is their product, and the derivative of f times g is the derivative of the first times the second, plus the derivative of the second times the first. And it turns out this formula, sometimes called the Leibniz rule, is the defining characteristic of what it means to be a derivative. Okay, so let's check that this works by using our example above. Again, let's take f of x and g of x to be x cubed with derivatives 3x squared. Applying the product rule as written gives us this. And plugging in everything, we get 3x to the 5 plus 3x to the 5, or 6x to the 5, which is exactly what we were supposed to get. Let's do a slightly harder example now. Let's find the derivative of x plus 1 e to the x divided by x. Now there are a bunch of ways that you could do this. For example, you could expand out the x plus 1 term and do some cancellations with the x in the denominator. That would absolutely work, and I suggest that you try it. I'm going to do this a different way. Let's write k as the product of 1 over x and x plus 1 e to the x. Okay, so I'm thinking of everything in these square brackets as being a single function. You can name each of these functions if you like, but I'm just going to write out the product rule using the derivative operator like this. Now everything on the left is known, right? We know that the derivative of 1 over x is negative 1 over x squared. On the right, though, we don't know the derivative of x plus 1 e to the x. So let's call this equation dagger so that we can come back to it a little bit later. Now we need to compute the derivative of x plus 1 e to the x. And luckily we can do that with another application of the product rule. Okay, so again, instead of naming these functions, I'm going to write out the product rule just using the derivative operator. These derivatives are pretty quick to find. And if we want, we can factor out this e to the x and write it as x plus 2 e to the x. So let's plug that back into Dagger at the top of the screen. I'm also going to evaluate the derivative of 1 over x in the first half of the equation to get this. Now we're technically done, but there's a few more simplifications we can make. Let's factor out an e to the x over x squared from everything, giving this nice simplified form right here. So with the product rule, the number of functions we can successfully differentiate has been substantially expanded.